Just a moment. Yeah. Yeah. Hussein, please start your presentation.
So, do you have my slides here?
Yes, yes, I can see it. Okay, I can see it, and now I disappear.
Okay.
For a while.
Okay. Thank you so much, Sasha. Hello, everyone. I'm Hussein from American University of Kurdistan in Duhok. I'm so happy to be here today with you, and it's an honor for me to be a part of this series of talks. I was a PhD student at this school from 2012 to 2016, which was jointly supervised by Sasha and Mark. I miss everything from that school. Very friendly staff, lovely environment. I would like to thank UEA and the school for everything they provided for me during my stay. It was my favorite school, and it was one of my best experience in my life. And I do recommend the school for anyone who is interested in doing research in math. Well, on this occasion of Mark's retirement, I would like to congratulate Mark and say a happy retirement, Mark. And I have this picture to share with you, Mark. So this was the last gathering. We had some of this gathering. I think the audience knows these faces. So Sasha, Tanya, Mark. This is my wife, Mina, and that's me. So I think that was the last gathering, and when I was about to come back home, I did my viva. And for me, Sasha and Mark are more than just a supervisor. They are the source of inspiration and motivation for me. I cannot express my gratitude towards them. Thank you so much for everything. And I'm so happy that I'm still working with you. It's an honor and privilege for me. And Mark, I hope you enjoy this end and you enjoy the start. I hope now you have time to do the things that you love. I know that you will love to explore more the history of math. So I wish you all the best. For me, you are just a great picture of humanity. I have seen many beautiful things from you, and I'm so happy that I was your student, and I'm still in contact with you, working with you. Thank you so much for everything. Well, I'll start by motivation of my work, and then give an introduction, and then the formulation, some asymptotic approach, and the result. So the motivation behind this work is that usually, because my PhD was about the effect of gravity on fluid structure interaction. So there are several phenomena in fluid structure interaction that affecting this impact, but they are usually not included in the modeling, like with surface tension, gravity, viscosity, and turbulence. But for gravity, we can neglect the gravity when the acceleration of the liquid particle is much more than the acceleration due to gravity. However, if this acceleration, if this is comparable, then we can we have to include gravity. So it's not clear and it's not obvious what's happening during the early stage. We cannot say everything through the Froude number. Usually people that just use this to neglect gravity, but we are going to show that this is not the whole story, and we're not aware of any theoretical study to picture everything, what's happening exactly. And we were motivated by some numerical and experimental work. So, for example, Steve and his colleague, they in 2005, they studied numerically using a CFD package to investigate the effect of gravity for a water entry of a semicircular cylinder, which is penetrating the water. And so they include in their computation the surface tension, gravity, and turbulence, I think. And then they perform their computation by including or switching off this parameter individually, and they found that the gravity is the only parameter which is significant. And I think they found that this gravity is affecting this slamming force coefficient by 23%. Some similar result recently by Tanya and Sasha as well. They found similar results on the force due to gravity. Sun and Falkenstein in 2007, they also studied the effect of gravity for a planning vessel with different speed. So they compare the effect of gravity for a moderate speed and high speed. They said that for a high speed we can neglect the effect of gravity. However, when the speed of the vessel is moderate, then you have to consider the effect of gravity. And they found that the gravity is not affecting only the surface elevation of around the hull, but also it's affecting the dynamic of this surface. And we have found something similar to this as well. And experimentally, these people, they found similar result when they worked for us wedge entering water. So that was the motivation of our work, and we know that these effects are small, but it's very important to picture them and to show the order of that influence. So in my PhD, we worked on two problems. One was solution inside a tank. So this is an LNG in a container, which is hitting the walls and the lid. So we studied the effect of gravity when a standing wave hitting the lid at the center, and we found the effect of gravity on the pressure distribution, the wetted size, and on this contact point and on the free surface. I think we did something numerical as well. We found similar results. But the second part was about the blunt body, which is entering initially calm water, which is solid, and then it's going to penetrate this water, and you have the displacement. So I'm going to talk about this part of my PhD, which is recently published. Then I have the effect of gravity as well for this jet, but for this presentation they are not included. And I remember we studied the effect of gravity for different part, how it's affecting the energy in different part of this profile. Then that's our paper, which is recently published in Journal of Fluid Mechanics. And so the problem is that we have a blunt body. This is the position of that body, which is penetrating water. It's parabolic and it's in time. So if we can get this linear scale for the flow, if we using that fact that the very early the contact point due to Karman and due to Wagner, they are very close, then we can get this linear scale of the flow, which is very smaller comparing to the radius of curvature of this body. So this study is restricted due to some condition that I'm going to show you. So we use that scale to non-dimensional the variables and the unknowns of this problem. So this is the formulation of the non-dimensional formulation of the problem. So we have three non-dimensional parameters here: epsilon and this delta, and this is a surface tension parameter. So these are the initial condition, and we have this initial condition for the contact point when the body is touching the surface of the water at a single point, and these are the Farfer condition. So the main three parameters or non-dimensional parameters in this study, there are the surface tension, non-linearity, and gravity parameter. So we know that this parameter is small compared with the fluid inertia. However, we restricted ourselves to the condition that it's still stronger than this nonlinearity parameter and the surface tension, then it leads us to this stage of the impact. We have the same when Greenhow always numerically shows that having this condition, we can neglect safely the gravity effect of gravity on the impact. I think this half was won before by Mackey, but Greenhow made it half, and it's clear. It's not clear how gravity is affecting, because different people, they getting different results, and it's very important to understand exactly what's happening. So if we neglect the effect of nonlinearity and surface tension and having the delta in the formulation, so this is a linearized formulation of the problem with counting for gravity, and this is a Wagner condition for our problem. Using this displacement potential and Wagner condition, we can have this formulation, and I'm just skipping this calculations, and to include the effect of gravity and using the asymptotic analysis, we use this threshold variables. So this is when the contact point is counted without gravity, and this is when gravity is accounted for. Then we use this asymptotic expansion for the unknowns, and we rewrite the formulation. The Laplace and Farfel condition are here as well. And at the leading order, this is the solution, which is previously was found by Korobkin and Hobison. And to find the first order displacement potential and to find the coefficient, we need to use this self-seminar using boundary conditions. We can rewrite this displacement potential in terms of this self-seminar variables. So we have to find this mu, which is helping us to picture what is happening regarding the contact point due to gravity. So using this complete displacement and rewriting the formulation, and analytically we will get this value for the mu, which is very small. So it's saying that if you look at this, this is a equation for the contact point. So we see that the effect of gravity is very small on the contact point. And this is a picture. Solid line is the size of the contact region, or the size of the wetted region with without gravity, and the dashed line is when gravity is counted. It's clear that as time goes, the gravity becomes important, but we can see that the effect of gravity here is small. So to find the effect of gravity on other unknowns on the pressure and surface elevation and force, I have this picture to share with you. So we found that for the pressure correction due to gravity is square root singular as well. Then we can write this pressure in this form, and we see that this is the order of the correction due to gravity on the pressure, which is clear that the effect of gravity here is small when the time at the early time. However, it's not in contrast to the contact point. The effect of gravity is very important on the pressure correction. So this is the pressure where, in the classical Wagner problem, and here I'm showing the three lines. So the solid one is the pressure correction due to gravity, and this dashed line are the correction, the hydrostatic correction. So it's mainly the correction is the hydrostatic correction due to gravity. However, this is the difference between these two curves is the dynamic correction due to gravity, which is small here. And but we use this technique to show how gravity is affecting dynamically the problem as well. So which is this technique used by these people. So they use this modified hydrostatic pressure to subtract it from the correction pressure correction to know exactly how gravity is affecting the dynamic component of the pressure. So we see that if you do this, then this at the center of the, so this is the weighted size. You see that at the central part of the weighted size, it's almost this gravity is not affecting dynamically the pressure. However, after that, we see that close to the contact point, the pressure is affected dynamically as well. So gravity is affecting the dynamical of the flow, and maybe this is also due to the results that I'm going to show by the change in the surface elevation. And this is the dynamic component of the due to gravity. So we see that close to the contact point, again, says gravity is affecting the behavior of the pressure distribution. Then for the hydrodynamic force, so we integrated the pressure, and we get this result for when it says that the gravity is increasing the force, and this is the order, which is the same in what we have for the pressure. So this is the surface elevation. I'm going to show you how gravity is affecting the surface elevation. So the solid line is the correction due to gravity on the surface elevation. The dashed line is the surface elevation in similar self-similar variables without gravity. So you see that we have some negative close to the contact point. So this is one represents the contact point. Close to the contact point, the correction due to gravity on the free surface is negative and becomes positive. It means that at some distance from the contact point, gravity is pushing up the surface elevation, and close to that contact point, the gravity is bringing down this surface elevation. And the same result was found by Mackey in this year. So if I show you here, this is the body. So it is penetrating to the water in time, and this is a very early stage. And now we can see the difference between the two lines, the solid one and the dashed line. The solid one represents the surface elevation without gravity, and the dashed one is when gravity is included. So we see that the gravity is pushing down the surface elevation close to the contact point. However, there is a rise in the level of the free surface. So it means that gravity is positively rising up the surface elevation some distance far from the contact point. So this was the result that I was going to show you, and I think I'm done here. Thank you so much for your attention.
Thank you very much, Hussein, for your very clear presentation, nice presentation. We have time for questions. We have enough time for questions. No questions. Yeah, Mark, please.
Hello, Hussein. Thank you for your talk.
Hello,
you
Mark.
have some interesting results to share here. And for this impact on the lid of a container, it's interesting that you found that the force is increased by the presence of gravity. I think that's right. Certainly in some places, the pressure is increased. I think in the center of the region, the pressure is increased when you include gravity, and although it's decreased elsewhere. So I think that's a very nice result to have come out, because it's quite counterintuitive.
Yeah, Yeah, so actually this talk is about the water entry problem, but yeah, for the solution inside the tank, we found very similar result how gravity is affecting the force on the water region. Yeah.
Thank you.
Hussein, following this question from Mark, in the case of water entry, what you mainly touched, the gravity is acting down in the direction of body penetration. So when in the case of your first slide, when the wave or sloshing impacts the ceiling of the tank, then the gravity is acting in opposite direction. So possibly we should expect that all your results could be valid, but with say delta or other parameters changing from plus to minus, and then say the gravity, the total force will be decreased by the same amount what you showed, but decreased, not increased. And then also in terms of the size of the wetted area, it could be different, but could be not. I don't know how it will be. So the change in direction of impact with respect to direction of the gravity, it could be non-trivial in this sense. Yeah.
Yes, I remember I during my PhD period, I remember I started to do some comparison between these two different but similar impacts. Gravity is affecting what are the similarities and what we have different. Actually, if we look at the contact points, we see that the gravity has the same effect as the contact, which is very small. But for the pressure, we have some different contribution from the gravity for the and for the force. But as you said, if we just sometimes for the force, for example, we know that for the solution, the force is reduced, but here we have increase in the force. So maybe, as you said, if we just multiply by a constant, then everything is going to be similar. Yeah, it's very interesting to. I remember we did something close, but we stopped. We get busy with numerical part of this. I remember.
Yeah. Yes, you are right. You're right. Yeah. Right. Also, it's just comment about your work that this is interesting problem from kind of mathematical point of view. You know, there is the problems with so-called small small denominators. So this is problem when the external force is small, but if the denominator, some kind of operator of the problem is small as well, then the response of the system is large. So that is the kind of one of the explanation, or it's very related to resonance phenomena. But anti-resonance is less familiar, so it's possible that even large external force doing nothing for the system. And that is the case where the kind of determinator or norm of the operator is large. And it seems that this is the problem, and this is why it was interesting for us, for Mark, as people working in School of Mathematics, that in this case, it was well known that many effects like viscosity, surface tension, gravity doesn't change significantly the nonlinearity, doesn't change significantly the size of the wetted area. Wetted area in computations compared with the theoretical analysis, what you did, it's is doing just the same, is giving just the same. So the results are very similar. So it was a kind of puzzle. Why it's so? even the gravity, you can reduce the speed of impact significantly, such that gravity is important, but actually it doesn't. So you was talking about the Fruit number. Even Fruit number is about 10. The effect of gravity is 0. And that is about, this is what in particular was discovered, that coefficient mu, which is the very small. So even if the effect of gravity formally is important, actually it's not. And the idea of this, okay, simplified analysis, which could be limited application, but it's showing small, no, denominator, small denominator, right? So this shows kind of, not shows, but discovers mathematically why it's so. So we discovered that mu parameters, which is small, and actually it's not a Fruit number, but Fruit number multiplied by something like 1000. That is important, or not multiplied, divided by 1000. That is important. So that was the interesting finding from the point of view of mathematics. So, okay. So any other questions? Any other questions? No. Yeah, it's 3 p.m., so people are leaving. But I have one comment for Theodosis. So thank you very much, Hussein. I stop your recording.
Yeah, thank you so much.
Yeah, thank you. I stop recording and then I'll